Good evening, Mr. Turner. Alright, welcome to Pascal's Triangle with Ashley and I.
Hello.
Yeah. Alright, so I just want to say to begin, we really enjoyed this project. I learned a lot, and I have always loved Pascal's Triangle. I really wish I had learned about it. Oh, wait, no, I learned about it in 4th grade, so pretty early. But yeah, this project was a lot of fun to learn about.
Yep.
So, let's get into it.
Alrighty. Ooh, there we go.
First, we'll start out with a little history. Pascal's Triangle was half created by the one who takes most credit for it, Blaise Pascal. However, many hundred years before, the Chinese had actually discovered a similar pattern. As you can see in the picture below, the pattern of the ones being on the outside and then going inward, down, and having D2s, 3s, 4s, and so on and so forth. Basically, evidence of this was found in Suyun Yuxian, or meaning Precious Mirror of the Four Elements, which was written by Chu Xian.
Alrighty. The next piece of history about Pascal's triangle was the quincunx. This is a machine built in 1303 by Sir Francis Galton. It's made up of pegs that are in the shape of Pascal's triangle, which is 1, 2, 3, 4. And basically what happens is you drop a ball down the top and then it'll fall into one of the slots at the bottom. And at first the results may seem very random, but after you collect them and graph them, they actually turn out to be the shape of Pascal's triangle, which is also very interesting.
Anyway, down to the man himself, Blaise Pascal, the one who takes most credit for inventing and discovering Pascal's triangle. It is named after him, his last name. He does take most of the credit due to the fact that he was the one that discovered many of the properties and a lot of the applications, many of the patterns inside of the triangle, and expanding further upon it as to what the Chinese had found many hundred years before.
Alrighty. The next topic that we're going to cover is the patterns of Pascal's triangle. One of these is the powers of 2. This is that the sum of each horizontal line in the triangle will be double the sum of the line before it. So, such as our example is row 3 is all of those numbers add up to equal 8, and then row 4 they all add up to equal 16. This also turns out that each horizontal line is then a power of 2, starting with the first line as being line 0, which can be seen in this picture right here. And it makes sense that all of them would be double each other because you're multiplying 2 again, so 16 and 32 and so on and so forth.
Right, and as we go along, many of the patterns we'll be starting with row 0 being the first number 1 at the top. The next pattern, it really helps with, if you want to just try to draw a Pascal's triangle from scratch, the sum of numbers below two numbers. Basically take any number on Pascal's triangle and the two numbers below it, the two numbers that are next to, the two numbers above it that are next to each other will add up to your original number. Which makes it really easy just to go down and find every single number without doing any other real calculations. For example, we have rows 3 and 4. The number 4, the two numbers next to each other above it are 1 and 3.
Yeah. This is a really good way to make the triangle from scratch. I'm not sure if that was said before, but if you don't have it already, it's a really good way to sort of figure out the pattern. Alright, the next one is symmetry. Basically, when split vertically down the middle, Pascal's triangle, the right side will affect the left side and vice versa. It's a really good way to, if you only have one side of the triangle figured out, then you have another way to figure out the other side. So this can be really helpful if you only want to figure out one side with the sum of numbers maybe, and then just kind of flip it over to the other side.
The last pattern, or the last big pattern, is the powers of 11 rule, where each line, if you line up all the numbers together, you'll find that that line will be a power of 11, starting with 0, of course, with line 0, row 0 being 11 to the 0 equals 1, and 11 to the first equals 11, and so on. Of course, as you get into larger numbers, this pattern isn't going to work, so the way you would figure that out is to move the first digit of the double digits into the digit above. Like 1, 5, 10, 10, 5, 1 would become 1, 6, 1, 0, 5, 1. And this can continue on downward, moving digits. Before I move on, some of the more obvious patterns, looking at Pascal's triangle, if you could just go back
Yeah, sure.
to one picture. On the outsides, it's all ones on the outside, and then the next row in increases by ones going down, and then increases by just more going down, but simple patterns in order to easily make the outsides of a Pascal's triangle to get you started is all ones on the outside, and then increasing by ones on the next row. That's just a helpful pattern.
Alrighty.
Now to some applications of Pascal's triangle, such as probability.
Alrighty, so the heads and tails probability, it's basically a 50-50 way to figure out like things that are 50-50. Depending on the line number that indicates the number of tosses, the numbers in those lines will indicate the number of ways the tails and heads can be arranged. Such as if we take the third line, there is one way that you can have all heads and one time you can have all tails, but then there are 3 chances that you could have mostly heads or mostly tails. So basically there's 3 ways that you can arrange heads, heads, tails, and 3 ways that you can arrange tails, tails, heads, such as in the 4th line. There's even more there, so that's where you get the pattern from. And I really like this, the one to the right side, and it explains it really well in this statement right here. On the 6th toss of the coin, there are 64 possible sequences, only one of which will be 6 heads and only 1 6 tails, which is right here, which I think really explained it very nicely, because right here it shows the number of possible sequences. Right,
the next application. Pascal's triangle is huge with the application of combinations. Basically, combinations help you figure out how many ways a certain number of objects can be combined. The way that Pascal's triangle can be used, you take the total number of objects that you have for your combination and go down that many rows, and then you take the number of objects you want to choose out of that total number and go over that many rows, such as, if you can zoom into the picture, if you had 5 items in total and you wanted to find how many combinations of 3 of them, you would go down 5 rows, or down to the 5th row, not including the row 0, and over 3, and you would find that the answer is 10. So basically, what I was saying earlier, I really wish I had learned Pascal's triangle a lot earlier, because helping with combinations definitely seems like a lot easier this way. That would have been really fun to learn earlier.
Alrighty. The final one is binomial expansion, which is basically x plus 1 to a power, or in the bottom picture they have a plus b to a power. Basically, for example, we put the 5th line, and this would be x plus 1 multiplied 5 times, and once you take all of the variables out, it should give you the 1, 5, 10, 10, 5, 1 that it shows in the bottom line of the triangle and the picture there. Alrighty. Next is the formula.
On to the formula. It's the same as combinations, like I said before. Pascal's triangle has a lot to do with the application of combinations. It actually has the exact same formula. However, in this case, the n stands for the line number and k stands for the places across. So n would be the total number and k would be the number of objects you're choosing out of that number.
Alright, the next is the name of the formula. The formula is usually called n choose k. The numbers of n and k are then represented in Pascal's triangle with n on the top and k in the bottom in parentheses. Here's a picture. Again, we're starting with the first line as line 0, and then actually each line in the each first number in each line is also considered 0.
And just like combinations, the formula is represented in two different ways, C of n comma r and then n cr. These would just be normal in an equation.
Yeah, it's kind of like f of x or y for a function. It just basically goes in front to show what you're putting into the equation. Alrighty, finally we have our connections to other math topics, such as the Fibonacci sequence. This is a pattern in which any number and the number before it, the sum is then the next number in the sequence. So 1 plus 1 is 2, 1 plus 2 is 3, and 2 plus 3 is 5, and so on and so forth. It can be found in the triangle by starting with the number furthest to the left, which will always be 1, and then going up a line and then over a space until you get to the rightmost number, which will always be a 1, and then you add up the sum of all of those numbers. It's really complicated. It's really complicated to explain, and I think it's easier to just show with this picture here. I really like how it uses the colors to indicate it, so that you have the 1 and the 1 and the 2, 3, and you can see how they added those up with the colors here. Alrighty.
Next pattern is one that's kind of simple. It's called if you color all of the odd numbers in Pascal's triangle one color and then all the even numbers a different color, it would turn out to resemble the form of Sierpinski's triangle, which is basically you take a triangle, cut it into 4 equal parts, take each of those triangles, cut those into 4 equal parts, then take those, cut into 4 equal parts, and so on and so forth. Mm-hmm. It really doesn't have much of a significance, but only a resemblance to Sierpinski's triangle.
Alrighty, the last one is Mersenne numbers, which are prime numbers based off of the formula 2 to the n minus 1. This is shown in the triangle by, I think it shows it really nicely in the picture. If you add up all of the numbers up to a line, and then that should equal 2 to whatever line number that is, minus 1. So it's kind of scratchy, but if you see in the picture, all of these numbers should add up to 31. And then it's a little hard to see, but the equation over here shows 2 to the 5th minus 1 equals 31.
So in conclusion, Pascal's triangle can definitely be found in many places, and a lot of other math problems can be found in Pascal's triangle, such as a well-known one is like Fibonacci's sequence, and a lot of patterns can be used and simplified in Pascal's triangle, such as combinations. So in all, Pascal's triangle is really relative to a lot of different math topics, and can be used in lots of different ways.
Alrighty, so that's it. Here are some of our sources that we used, and I guess thank you for watching. And
yeah, thanks for watching. We had a really fun time, and we learned a lot of doing this.
Yes,
so
most
thanks for giving us this opportunity.
Thank you.